Ocean acidification can be described as the effect of increasing levels of atmospheric carbon dioxide on ocean carbonate chemistry. The increased levels of atmospheric carbon dioxide is due to human activities related to the burning of fossil fuel and changes in land use. When carbon dioxide combines with water, it forms carbonic acid, which can then dissociate to form bicarbonate and hydrogen ions. When the seawater concentration of hydrogen ions increases, the concentration of carbonate decreases due to the conversion of carbonate to bicarbonate. An alteration in the concentration of carbonate in seawater affects the saturation state of calcium carbonate compounds, which disrupts the ability of many marine species to build their shells and skeletons from calcium carbonate. Due to the relatively recent increase in atmospheric carbon dioxide, the world's oceans absorb more than 25% of the carbon dioxide emitted into the atmosphere by humans, which causes an increase in the ocean acidity and potentially negative impacts for marine life. Coastal regions are particularly vulnerable to the impacts of ocean acidification due to the prevalence of upwelling, the inputs of freshwater nutrients, nitrogen, and sulfur. Upwelling of deep waters near the coast is enriched with carbon dioxide from the deep waters that had encountered the carbon dioxide from the atmosphere in the past, deep water respiration processes, and the lack of gas exchange with the atmosphere. The coastal waters off the east coast of the United States and regions such as the coast of Maine are more susceptible to changes in ocean acidity due to freshwater inputs, which cause a variability in the concentration of dissolved inorganic carbon, total alkalinity, dissolved and particulate organic carbon, and nutrients. The input of fresh water from climate-induced changes in glacial melts and high-intensity precipitation creates conditions that dissolve calcium carbonate structures. Nutrient runoff increases ocean acidification by increasing the incidence of phytoplankton blooms, which when dead are consumed by bacteria that respire carbon dioxide and in effect increase ocean acidification via feed-forward mechanisms. Water temperature strongly influences ocean carbon chemistry because the solubility of carbon dioxide increases proportionally with a decrease in water temperature. Therefore, cold, high-latitude surface waters, such as off the coast of Maine, retain more carbon dioxide and carbonate compared to warm, low-latitude surface waters. Cold waters become undersaturated with calcium carbonate, since carbonate is more readily dissolved in cold waters, which leads to a corrosive state in which mineral dissolution is favored with respect to calcium carbonate. The incidence of corrosive conditions has been documented extensively in the high-latitude system of the northeastern Pacific Ocean, which borders Maine, due to the low buffering capacity against changes in pH. It was projected that by the end of the century, under the higher scenarios, open ocean surface pH is predicted to decline from the current average of 8.1 to the proposed average of 7.8. This projection suggests that the volume of water undersaturated with calcium carbonate could increase from 76% in the 1990s to 91% by 2100, which would affect the lives of several marine species. Under the same scenario, the average global surface ocean acidity has been predicted to increase 100 to 150% by the year 2100. This decrease in pH is proposed to have a profound effect off the coast of Maine, effectively disrupting the life cycle of calcium carbonate-containing organisms, which has the potential to have a negative impact on all of the species that consume these organisms and the organisms that consume those organisms, including humans.